Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure today to host Rich Wolski from the University of California, Santa Barbara. Ooh, I wrote the wrong thing on your form. Rich has had an interesting career in scientific and high-performance computing. We were just talking about Sisal and how that was the language that should have won out over Fortran, but it didn't.
May yet, though.
It may yet. We may again in the future. And Rich has done a lot of work in the grid space and is now actually working in elastic computing. I guess there isn't really a better term yet to describe it. So he's going to tell us about his version of EC2.
Good morning, everybody. Thank you for coming. I realize that you've probably had a number of opportunities to see faculty people talk to you in the last few days. And so, but nonetheless, I'm here, and I wanted to talk to you about a project called Eucalyptus, which we started very recently. This project is not very old. The actual coding on it started February 1st, and that'll be perhaps more interesting as time goes on. Okay, so let's start with a little bit of background. I'm an academic. I work at a university with very talented people who appear on that slide and will show up again at the very end. And we've been doing, as Jim said, grid computing. And grid computing at all sorts of levels, at the research level, at the infrastructure level for the National Science Foundation for a long time, basically since 1994. And that, if you've been paying attention, is before the term grid computing actually existed. That came out in 1997 with Ian and Carl's book. So we've been at this a while. And along about January of 2007, this notion of cloud or utility computing or elastic computing started to take off. And from the perspective of an academic, that's kind of interesting. We've been doing distributed computing where, many of the principles that people in cloud computing espouse regularly have been tenets for a long time. And suddenly, you see like 527,000 hits for the term cloud computing in Google. That's April of 2008. Google did not define the term cloud computing before October of 2007. So if you go from nothing to that, even if you do control the search engine that's reporting that, something's going on. And what we saw in the press was a lot of people were talking about essentially the same thing under different terms. Cloud computing, elastic computing, utility computing, depending on which vendor and what day. And there's a lot of commercial activity. These are logos that I just happened to scrape from companies that all claim to be doing cloud computing. Now, we can talk about interesting questions like what is cloud computing and how does it differ from grid computing? And I'd love to do that ad nauseum. But the observation I wanted to make here is there are a lot of people who think they know and also think that there is commercial value in doing whatever it is that we think we want to do. Now, as an academic, that's great, but as Dan Reed likes to say, I have the sense of déjà vu all over again, which is, okay, you have a lot of people building things, you have a lot of commercial excitement over something. What is it? How does it work? Right? There are some very fundamental questions that we do not seem, or they do not seem, to be addressing at this moment. For example, what can and cannot be easily hosted inside a cloud? Now, after grid computing experience, I can say there are some things that work really, really, really well inside a grid, and some things that don't. I suspect that's true for cloud computing. What are they? There are a lot of other, what cloud computing is used for at the moment, is mostly web service hosting. Right? There are some people who are doing large-scale Monte Carlo and embarrassingly parallel things, but for the most part, what's going on inside cloud computing is web hosting. Okay, great. Web hosting is good. There are lots of other things people want to do with large-scale systems. Scientific computing is one of them. Now, a lot of people say, well, yeah, there's not a lot of money in scientific computing. Okay, but there is a lot of money in data assimilation. There's another revolution coming down the pipe in addition to cloud computing, and that is sensors. Everybody is talking about putting sensors in everything. everything, the walls, your pets, your children, all these kinds of things are going to be wired up. That's not a joke. You want to know where your kids are. You want to know where your pets are, right? I mean, and so, yeah, but it is kind of funny. And you want to be able to compute over that. You want to be able to make inferences against a rain of data that is going to be coming out of pretty much everything that you talk to and have contact with. Does that work in a cloud environment? We don't know. There's these sort of society-changing technologies. Multiplayer gaming. You might want to laugh about that. They did a study. They found out that amongst people in their late 20s, the biggest consumers of multiplayer games are parents. And that's because they use it as a way to bond with their children. Right? This is changing society, and it's a technology that has a tremendous amount of commercial value. Does that run in a cloud? We don't know. Right? There is another cloud out there. Right? Maybe it's a thin cloud. We don't really think about it. It's your cell phone network. When you pick up your cell phone and you figure out where that Chinese food restaurant is, you're talking to a cloud. You don't know where that computation is taking place. You don't care. Right? That is kind of the definition of cloud computing, or software as a service, or whatever you want to call it. This has been around a long time. These people have infrastructure in place. It's actually more cloud computing than cloud computing in the sense that they even do bandwidth provisioning and dynamic reallocation of bandwidth, which most cloud systems do not. So in terms of architectural characteristics, this is here. It's hard. Things are moving around. How does that couple with cloud computing? We don't know. So when you don't know, and you're an academic, what you tend to want to do is go get a piece of software that allows you to experiment and otherwise understand kind of the inner workings and the do's and don'ts and so on and so forth. And that to us as some sort of open source cloud infrastructure, right? It has to be simple, yeah, because I'm simple. It has to be extensible because whatever it does today is not what we want to know about. We want to know about what it can do and it cannot do. It has to be based on widely available and popular technologies, because if you need some very special and expensive technology, it's extremely difficult to work with. A good example of this is Flash. I got a bunch of students who want to do things with Flash. A Flash server is $10,000. I don't have $10,000. Yes, there is an open source version of it called Red 5. No, it doesn't work very well. So if you base your scientific infrastructure on something that is really expensive and proprietary, you don't get a lot of uptake. And what we want is uptake. And it has to be easy to install and maintain. And that's because in university environments and other research environments, other than places like Microsoft Research, your system administrators are the scarce resource. And if this is hard and painful, you don't get to do it. So then we said, okay, great. I have a research group. So, some members of this audience have been in that research group. They know that this to be a fact. Whenever I have a wild hair like this, I walk into the research group and I say, okay, guys, you need to go out and find me X. And in this case, I said, you need to go out and find me the open source cloud infrastructure so I can initiate this research program, and we're all going to go off and do this for a while. And they said, well, Rich, there's really not a lot of choices. There's something called Nimbus. It's actually the Globus Virtual Workspace Service. Globus is a grid computing infrastructure project. It's been around for a very long time. It's currently at Rev 4. We've worked with Globus at Rev 1, Rev 2, Rev 3, and Rev 4, so we know an awful lot about Globus. And they have a mechanism built into it for allowing you essentially to provision batch scheduled systems with virtual machines. So if you wanted to launch a batch job, a parallel batch job where the individual processes of the batch job were VM instances, you could do that with Globus Virtual Workspace. And then they realized, well, gee, that's something we could use to build a cloud. And so they stood up something called Nimbus on top of that mechanism. And so, you know, if you buy GT4 and all of the pieces that it comes with, and you have an HPC environment, high performance computing environment, you can layer their web service tools on top of that and get something that looks like a cloud. And they've been doing this for a while, and there's documentation, and it's great. This, though, is fairly complicated. Right? Taking apart GT4 and understanding what it does is not for the faint of heart. We've done it. We actually are GT4 proficient, but it's not a really great way to encourage folks to experiment, at least on the internal level. But in terms of usage, it's quite good. There's also something called Anomalism. This is an open source company. At the time we started this project, they had no software on the web. When we announced Eucalyptus, they very quickly released their software. I don't know if that was coincidence or not. It turns out to be extremely complicated as well. They have a baseline open source version written entirely in Java. It's not web services based, but they have just a plethora of features that you might want, and file systems and federation mechanisms and so on and so forth. And again, I think their approach here is to really give you kind of the baseline technology and then hope to sell you the stuff on top of it, and it's fine. I mean, there are lots of people who are interested in this, but again, it doesn't serve this sort of simple, easy to extend, easy to understand need that we think we have. So we decided to do it. We decided to do Eucalyptus. Eucalyptus actually does stand for something. It stands for Elastic Utility Computing Architecture Linking Your Programs to Useful Systems. No, we did not come up with the acronym before the name. One of the few functions, positive functions, useful functions I serve in my group is to be able to make acronyms out of names that people come up with, and so there you go. But we made some decisions about Eucalyptus, which I think make it kind of unique. The first thing we did is we said, well, this is going to be based on web services. And the reason it's going to be based on web services are, A, we think that in most cloud environments, web services are going to be supported, right? We see a lot of web service hosting in cloud environments. Web services is really the key technology. We better be building this out of web services, right? The idea is that we're going to work with the open source web service infrastructure, and if that's the case, then it's probably Linux-based, at least for the moment, right? We can discuss why. Okay. Second thing is we're systems builders, we're not interface designers. That is a huge mistake that I think many systems builders make when evaluating their prowess in this space. And so we said, well, first cut anyway, we're not going to design an interface. Right? What we're going to do is try to figure out if we can support someone else's interface. And this has two important properties. One, we're not guilty of defining the interface. Two, we have a good sort of Turing test. We can run something against the existing system and then run something against our system and know, did we do it right? And so the system that we wound up deciding to mimic, if you will, is Amazon's EC2. And in particular, Eucalyptus doesn't have any of its own command line interface tools. You download them from EC2. So we are sort of insulated across the interface from from EC2. We don't modify those tools at all. And another sort of advantage, if you will, in terms of uptake that we didn't anticipate is there's kind of a cottage industry, maybe not so much a cottage industry, of companies that are building programming environments for EC2. EC2 gives you this low-level provisioning mechanism for virtual machines. It doesn't give you much in the way of higher-level programming support. And so you can come along and layer, say, Ruby on Rails on top of EC2 and sell that as a service, as RightScale does. If we're EC2 compatible, that tool should work with us, right? Okay. We wanted it to function as an overlay. It doesn't have to function as an overlay, but in an academic environment, if you come to your system administrator and say, gee, in order for me to do my research, you need to refactor all of your nodes to have this operating system, and I want to change your networking. And by the way, that security policy is inconvenient for my research. System administrator slams the door in your face and you walk away. So you've got to be able to come along and say, okay, you have an existing infrastructure. I would like to put this infrastructure on top of that infrastructure and do the following experiments. It may not work as efficiently as it could, but it cannot be invasive if you're going to tap very expensive overworked system administration resources initially, unless you have carte blanche, which most professors do not. So we wanted an overlay functionality, and in the same vein, what we observed, and this is we observed from the grid computing community, where we were really trying to get uptake. What system administrators in this space want is a tool that a user requests that requires a single button press to install and that they never hear about again, ever, right? GNUplot is such a tool. If you run a Linux installation and I go to you and I say, I would like GNUplot, the system administrator has some web-oriented or menu-oriented thing where they go, GNUplot. Something happens, they say, it's done, GNUplot works. And they never hear from me again about GNUplot. That's the goal. Okay. This is tougher for distributed systems, but if we're going to get people standing this up and running it, we've got to get at least close to that model. Otherwise, there will be just tremendous resistance. And from grid computing space, this is true. This is true in the infrastructure space. This is true in academic spaces. We've had a hell of a time trying to get folks to install and maintain the grid infrastructure we want, even when it offers all sorts of really important and powerful new functionality because of this issue. So, okay. So that's what we thought we did, or what we thought we needed. There actually are some higher level goals, some raison d'etre, if you will, for doing this. The first is hopefully obvious by now. We wanted to foster research in this area in the community. It's a little scary to me that you have this huge investment by these companies in wildly, potentially diverging technologies, and no one is really in a position to make statements one way or another about the fundamentals. Okay? That's the way this works. It is a big industry. There's lots of impetus. You want to strike while the iron's hot, but somebody somewhere has got to start thinking about what's really going on down underneath, and that should be the community. It shouldn't be a person, and there needs to be an infrastructure for doing that, and we're hoping Eucalyptus will be that infrastructure. It also turns out that there are other things in university and research environments that we perceive that may be aided by this. So one of the things that many researchers are interested in is, gee, how hard will it be for me to port my code to EC2? It's an interesting question. You could go and get an EC2 account and spend the money and do the setup or whatever. Providing a tech preview, providing an environment locally with all of the compiler support, with all of the system administration support, system administrators understand the local environment, so on and so forth, to, say, chemists who are then thinking about purchasing services from other commercial service providers, seems to have value. And we've had a lot of positive response from scientists who say, gee, that'd be great. I'd like to experiment with this before I go off and purchase services. There's the debugging question. Most science is done in the following way. You do an awful lot of very short runs that you know produce the wrong answer, so that you can figure out incrementally how to get to the right answer. Once you've convinced yourself you're going to get the right answer, you do a few very, very large-scale runs to get some answer that you then go off and analyze, and you rinse and repeat. So those small runs often require a great deal of analysis. You really have to understand what's going on at a fundamental level to figure out what's wrong. And cloud infrastructures, in some sense, make that harder. Right? It's a much more opaque interface between what's happening and what you're doing. And so in the debugging cycle, we think that there's a value to having this. Another thing we're really hoping for, and this is kind of pie in the sky, is just the Linux experience, right? Where you come out with a simple piece of software that essentially exports a well-understood interface, and because it's simple and it's written with common technologies, the community picks it up and begins developing with it. I don't know if that's going to happen, but it's certainly a goal we would, we thought about. What was not a goal, and I have to put this in as a disclaimer, was we were not building something that was intended to replace anybody's cloud service, EC2 or otherwise. And that's because if you're going to make an open source, portable, overlay-based experimental system, it is not going to scale to the levels that you want in a production environment. It's not. It's not that you can't make it scale. You're just going to have to re-engineer it. Okay, that's fine, right? If what happens is someone comes and picks up our software and builds something that looks like EC2, that may or may not be, a bad thing, but there will be so much re-engineering of what we've done, it's really not us, right? It's just conceptually us. And so this has been a point of confusion, and I just want to make it clear, this is not a replacement for anybody's cloud. Okay, so if that's the case, and I believe it is, then there's some significant challenges that one really needs to be able to overcome if you want to pull this off. There's extensibility challenges. There's the interface challenge, making it sort of work against someone else's test system. There's some significant networking challenges, security challenges, and packaging and installation and maintenance. And so we'll talk about those. Extensibility. The key to extensibility, we think, is simplicity. So the way that the system is architected is essentially in 4 components. There's a client-side API translator. This is something that understands web service emitted XML and translates it into a canonical internal language. And that language is itself transmitted around the system via web services. So every line you see on this diagram is a web service interface with WSDL. So that if you wish to replace a component, the interface to the component you're replacing is documented. It's documented in a way that you can analyze programmatically, right? So Amazon's EC2 tools issue their web service stuff to our translator. Our translator turns that into something that a centralized cloud controller understands. This is where all the SLA management happens. If you're not familiar with EC2, what EC2 gives you is something called an SLA, a service level agreement. You will get a Pentium 3 circa 2007 with 1 gigabyte of memory and 1 gigahertz CPU speed, 160 gigabytes of disk at 10 cents a CPU hour. Okay? That's their SLA. There are other SLAs you can imagine. That's a very simple SLA. It's just a rental model. It's not a lease. It's indefinite. As long as your credit card holds out, we'll rent that to you. Something has to understand that. Something has to understand the provisioning of that. And in our model, that's the cloud controller. The thing that actually does the provisioning is a little piece called the node controller. The node controller basically lives on each node, and it essentially drives the local virtualization interface. So if you want to instantiate a VM or tear down a VM or make networks and so on and so forth, you need a presence basically at all the execution sites. And then there's this piece in between, and that's because in most environments, IP addresses are a scarce resource. You don't have an unlimited set of IP addresses. These things all are NATed typically, and they live on their own network. And so you need some way to communicate from the inside world to the outside world, and there's basically a proxy. Now, once you've got this proxy here, there's actually a division of labor that makes sense in terms of efficiency and single point of failure and so on and so forth. And there is some artistry in the way we've architected the division of labor between these two, but it's not something you couldn't change. So this is simple. This is the dead simple interface, this dead simple architecture for building a cloud. I don't think you could make it simpler. Right? We've actually talked about whether we can do away with this piece. And you might be able to if this is fully functional, but logically there are those two pieces. Okay? And it's all built with open source web service technology. EC2 compatibility. The good news about EC2 is that they publish their WSDL, and they publish it in uncopyrighted form. There's no copyright as far as we can tell. Even if there was, we don't redistribute it, so it may be okay, we just read it. What we did was read their WSDL and then figure out, based on what we think Zen does, Zen is the virtualization technology upon which EC2 is built, how to translate that. And it turns out to be relatively straightforward, and I don't think that's an accident. I think the people at Amazon really knew that simplicity was the way to get scale out of this. And so they essentially made a very, very simple web service interface to Zen, if you will. And so we got everything in the 2008 specification except for static IP addresses and security groups. And this is because you need some more invasive networking than we thought we could do at the first releases. We know how to do this, and it'll be coming probably in the next month or so. There's also an abstraction inside Amazon called availability zones. And what this does essentially is allow you to have some more understanding of the topology that Amazon is using to host your virtual machines. For example, you may wish to have virtual machines living in 2 different data centers for availability reasons. If one data center goes down, you'd like the other one to be up. We've hijacked, in some sense, that abstraction, and we Eucalyptus essentially says that an availability zone corresponds to an individual cluster. So you can get a cloud allocation that spans clusters, or you can select an individual cluster in terms of an availability zone. And that can be expanded, but in the initial version, that's the way it works. We don't provide you tools. You download them from Amazon. And it turns out these tools, Amazon exports 2 interfaces, the command line tools interface and a REST interface, and we support that. And that's so these other programming abstractions and services for EC2 can work. With EC2, there's something called S3, which is their storage system. It's only for EC2. It's only used for image management, and we don't have at this very moment an emulation of that, but we are working on it. That'll probably be out in the next month as well. It's very simple. There's no rocket science in S3 as far as like the interface goes. So that doesn't look hard. A big thing though is that while Amazon does publish its client-side interface in great gory detail, it tells you nothing about how they administer this system. Nothing. We don't know what the administration tools are. We don't know what the monitoring tools are. Nothing. So we have to make this up for the open source version, since they're not going to come clean. And so we've done that. We've built a whole bunch of cloud administration tools. And user accounting, it turns out in our space, is harder than it is in Amazon space. No students have credit cards. So you basically have to be able to do something a little bit more elaborate than that. Right, networking. So it doesn't assume that everybody's got an infinite supply of IP addresses. And so there's really two kinds of virtual private network, if you will, that your cloud allocations get. When the cloud allocation comes up, what it sees is that all of the virtual machine instances in the allocation are on its own network. And that network is isolated from everybody else's network. Okay? So we have one that uses VDE. VDE is a software emulation of an Ethernet controller. And with Linux, you can actually, through TuneTap, jam VDE onto your system so that any calls to the Ethernet driver get bounced into this user space process. And then it makes, essentially, Ethernet frames and UDP packets and sends them out. So this is nice, because if you're working at this level, you can basically put up your own Ethernet in whatever topology you happen to be living in. The bad news is it's slow. And it's also CPU bound, right? Because you're doing this processing in user space. So if you live within a single availability zone within Eucalyptus, i.e. you're running inside a single machine, we skip all of that and we just run with the native hardware speeds. All right? And this sort of gives, it's the same idea of this topology exposure. Right? Just to give you a cartoon, if you have a cloud allocation that spans two different clusters, you need to use VDE to enable the local network that these two virtual machines see. And we tunnel that through SSL between the head nodes of the cluster so that there's no sort of exposure. You can turn this off, and there's encryption or not encryption for this. And the bottom line, but you get this very flexible, if slow, mechanism. If you live within one cluster, though, and you select that as an availability zone, then we skip the VDE parts. We just run on the native network. And to give you an idea of the performance drop, this is 100 megabit Ethernet. This is about MPI. By message size. So the way you read this is megabits per second, bigger is better. And this is the message size in an MPI message. And MPI is essentially a parallel programming abstraction for message passing that is very, very commonly used. And you lose about 25% on 100 megabit Ethernet to VDE for MPI. Turns out, though, that this is kind of almost an upper limit because you're really banging it into the CPU and not the network at that point. So security, great. None of this is going to matter if the system that we build is insecure. And so what we decided to do was call upon WS security and in all its richness to try to make the system secure. What does this mean? At the moment, what it means is that all of the Eucalyptus components authenticate with each other using certificates. So those certificates have to be installed in the right place, and building a mechanism for installing the certificates in the right place, in the right order, is tricky. But if that's true, and you trust Apache's Rampart implementations, because that's the implementation of WS security for Apache's open source web service infrastructure, then it is the case that you cannot spoof Eucalyptus processors into believing you are, or Eucalyptus processes into believing you are a Eucalyptus process. You cannot is a strong statement. It's you cannot up to the security of that system. There are some caveats. It turns out that the parts that run inside the cluster are written using Access2C and Rampart-C, and the parts that run outside are written using Access2 and Rampart. That's Java and C for those of you who are in the programming language space. And while they're supposed to be kept completely synchronized, and the Access2 parts do appear to be kept synchronized, the Rampart parts are just a little off. And so there's some hand-waving that goes on to try to make that work, and we've done it, and we're hoping the Rampart people will fix this problem, and if they do, then it'll be pretty clean. And you can turn on encryption. If you're nervous, so what happens is the authentication is done, but none of the traffic is encrypted. You can see the Eucalyptus messages on the wire. If that bothers you, you can actually make it encrypted. It'll just slow down. There's another thing that you need to do. When you instantiate a virtual machine image, you need to put the user's SSH keys into the image so that they can access the machine once it's stood up, the virtual machine, and we do that. And then we have this accounting mechanism, which is essentially web-based, where you go and ask for Eucalyptus credentials, And what happens is the cloud administrator gets an email saying, do you wish to issue credentials to this person? In EC2, what happens is you type in your credit card. They verify the credit card, and if the credit card is valid, they go ahead and issue the credentials. We have no such luxury. This brings up an interesting question in terms of accounting. If there are two clusters with two different user pools, what's the user pool for a cloud that spans those two clusters? It sounds easy, but your options are the union, the intersection, or none of the above. And there are good arguments for why it's none of those. There's good arguments for why it's each of those. So just understanding the accounting base in this space, particularly where we have Department of Homeland Security requirements having to do with identity, right? Students come from all over the world. Not all countries are considered equivalent in terms of trust, let's say. And so you've got to really be able to account for usage in an academic environment. And so this part actually turns out to be an interesting research question, although no one thinks it is. And then lastly, you've got to make this easy, right? You've basically got to be able to get it so that it can stand up like a Linux installation. And so what we did for the first cut was we went and we got a cluster configuration package called ROCks. This is done at the San Diego Supercomputer Center by Phil Papadopoulos. And it's essentially a Red Hat based. And what it's designed to do is to support the almost automatic configuration of clusters. If you're building a cluster, you have a head node, you have internal nodes, there's networking configuration issues, there's distribution, package distribution, so on and so forth. And they have these very, very sophisticated mechanisms for rolling that stuff onto your cluster. And so if we could package Eucalyptus for ROCks, in theory, you could tell ROCks Eucalyptus, and you would get Eucalyptus on your cluster. And in fact, that does work. What was less obvious to us, though, was that ROCks itself is hard to install. In our space, in the NSF supercomputer space, almost all the machines are configured with ROCks. We see a large user base of expert users. But what we got in terms of feedback from the community was, ROCks is really hard to install. Once I got it working, Eucalyptus works great. And so we said, okay, well, what we really want to do is also provide build from source. This is not one button, right? It's not really easy using shell scripts and autoconf and so on and so forth to make a distributed system one button install. And so right now what we've got is a bunch of instructions, a bunch of scripts, some rsync, and the hope that you've got some sweat equity in the game. But this actually allows you to run the thing on a single machine. We've actually done a single machine cloud. We didn't do this initially because we didn't think anybody would care, but you can run the whole thing in one DOM0 if you're Zen proficient, and you just have to do some port conflict stuff by hand, and we have instructions for doing that. So we've got source build, which should be hopefully very portable, but requires some energy, and we've got ROCks build, which allows you to roll this stuff out very, very simply if you're a ROCks installation. This is the technologies. We talked a little bit about Access 2 and Access 2C. There's some Java stuff. This makes the cloud front end both extensible and scalable. That's the web service stuff. libvirt is virtualization support. We'll talk about that a little bit. SOCAT is lovely network tunneling stuff in VDE. A few packages that you got to get, and you have to get them at the right rev level. So we actually distribute the right rev levels with the software. Okay, so we built that, and we put it out. And a bunch of people said, well, I want to play with it first. And so we said, okay, we're going to stand it up. So right now at UCSB, there's the Eucalyptus public cloud. And it's just a Eucalyptus installation running on a small machine. And what we've done is we said, okay, you can only run our images. There's a 4 virtual machine limit to any particular user. We lease you the time for 6 hours, then we kill you. And this is the big one. There's a reverse firewall, which essentially means when you get in, none of your virtual machines can make a network connection coming out. And that's because we were worried about the spam bot problem. This turns out to be a huge impediment. Why? Because the first thing that you want to do when you get a virtual machine is begin doing apt-get or whatever, and you can't. You actually have to do all your configuration out of it and push it in. We don't know how to get around this yet. We're talking to the security people. Maybe we're going to punch a hole in the reverse firewall for certain distributions or whatever. So this is kind of limiting the utility of this experiment, although we've seen quite a few people use it. This is the machine configuration. It's not very big. I mean, there's nothing more to say about that other than, it's not a super powerful machine. Now, what I wanted to do was show you, hopefully, a little bit about this. So on the top level here, and I don't know if you can see this or not, what I've got is staged a connection, the credentials essentially, for EC2. That's the availability zones that Amazon's EC2 currently exports. There are 3, East 1A, 1B, and 1C. In theory, if you host a virtual machine in 1A and 1B, 1A and 1B will not be able to go down simultaneously. We don't know if that's true in practice, since S3 seems to go down, and the storage may be the issue, but that's their idea. In the lower window, oops, sorry, kill that. I've got EPC. So what this is doing is it's running the same command, which is describe availability zones, except this time it talked to UCSB. We don't have quite as many availability zones. We have 1. But you can see that the format is about the same, and the important thing is it's the same tool. If you want to see what images are available, and the -O Amazon here says ones that Amazon makes available. That should generate quite a bit of output. There you go. These are images. These are actual Linux images that one can access if one has an EC2 account. They have an ID. This tells you a little bit about where they came from. This is actually what's called an XML manifest, and whether it's 64-bit or 32-bit, so on and so forth. And let's try that. And we also give you some images, fewer. So I won't go through the less than entertaining and somewhat slow process of starting up an image and SSHing into it. I hope you believe me at this point in this demonstration when I say we are interface compatible with EC2, right? It looks the same, it feels the same, it's the same tools. You just change the credentials and away you go. Okay, so let's talk a little bit about differences in performance. One very natural question is, well, gee, Rich, if that's the case, how does EC2 and the Eucalyptus Public Cloud, EPC, compare in terms of, say, machine-to-machine bandwidth? Well, here you go. The blue dots are EC2, and the green dots are EPC. And I have to confess, while I love Excel is a great thing, I don't know how to make a bar graph with error bars. And error bars matter. There actually are error bars on this. You can just barely see them here, but that's an important piece of information. If it's smaller than the dot, you know that the error bars are not that big. But one of the questions people have frequently about Amazon is the degree of variance. And so we are very careful about error bars. And the only thing I could find in Excel that would allow me to put error bars and height were scatter plots. Sorry. But this is megabits per second along the y-axis. And these are just 4 different categories. It really should be a bar graph. And what we see is that, in fact, if you stay within a single availability zone for EC2, you get around 450 megabits a second with a very narrow 95% confidence interval. If you go between availability zones, as you might expect, there's a slight drop-off in performance. This is the Eucalyptus EPC network performance. It's 1 gigabit Ethernet, and that's about as fast as you're going to go. With Zen. We've done the naked benchmark, naked Zen benchmarks. It's about as fast as you're going to go on the naked hardware. I think you can get maybe 0.5% more if you get Zen out of the way, but it's really hard to say whether that's statistically significant or not. So, and then this is what happens if you use VDE. And this number is actually wrong. It turns out VDE has 2 different configurations having to do with the way it authenticates. And for reasons we don't understand, if you use SOCAT as opposed to a cryptab, you get better bandwidth, even though there's no bandwidth, there's no encryption of the data going on. So it moves from about 30 megabits a second to about 90. This number should be about right there. We just figured that out last night. Sorry. So I didn't have time to change the slides. But in terms of orders of magnitude, it's about the same. So, so there you go. We're essentially getting about naked hardware. Now, the important thing to understand here is this is a very scalable system, right? That availability zone is, 10 to the 5, 10 to the 6th processors. This is, 8 processors. So there's certainly a difference in scale here, but it gives you some idea of where they are in the spectrum. This is, sorry, yeah?
What did you use to measure the TCP performance? Is that a
Hyperv, and that was, what's that? 256K and buffers.
And I assume that you wouldn't have had too much of CPU, interference,
Whatever it was, but if you did, you would see it in the error bars. If there was a lot of CPU interference, then you'd see variance somewhere. I mean, that's just dead on network performance. It really is. That's such a small 95% confidence bound for a number that big. So, right. Okay, this is ICMP ping round trip time. Smaller is better here, right? So this is milliseconds, so you want lower. EC2 1 zone, EC2 2 zones, again, what you'd expect, 95% confidence bounds. VDE, no VDE, and VDE. And yeah, this is what happens when your CPU gets involved, right? I mean, now you're running VDE in DOM0 while you're running a virtual machine as DOM-U. There's scheduling issues. We actually believe that VDE was an interesting first cut. It was the right thing to do to get something out, in 5 months. It's the wrong answer ultimately, and we can explain why. We'll talk about why. I have a slide about that. But the bottom line is this gives you just some feeling for what it looks like to run inside Amazon and Eucalyptus on your own resources. Not bad. Another question that you might ask is, how long does it take to start something up, an image? Okay. This is an inverted CDF of 65 image starts. So I apologize for this. There's always, if you're a stat person, you actually usually swap these axes when you do a CDF, but then you lose the fact that the y-axis is in fact the variable of interest. And so, so I've elected to sort of invert this. The way you read this is, say, 60% of the startups took less than 11 seconds. Right? So it's just an inverted CDF. The red line is EC2, and the green line is EPC for a single instance. So that's interesting. It's interesting for a couple of reasons. Well, let's talk about why it's not interesting. That difference I don't think is interesting. EC2 is big, very, very big. And so when you stand up an instance, the amount of mechanism that's probably got to run in order to get everything working while everybody else is getting something working is fairly large. So it's actually kind of remarkable that it's that small. The shape, the fact that we follow this shape, so carefully, that's interesting. Now, it's not enough data points to make any sort of inference about that. Although it could be, right? I mean, 60 is getting to the point where if something's unimodal and symmetric, that you might be thinking about it as a normal, at least with respect to the mean, and so that was kind of puzzling. If you go to 4 instances, you see a big jump in terms of the magnitude, but again, you get this sort of similar shape thing, and it's not clear there. And then when you go to 16 instances, now we start to see how having more is less, if you will, and we are 8 instances, I guess, and we start to approach EPC or EC2's performance. But again, the shape is very similar. So this is something we want to understand. Why is that? And is this a distribution that we can just explain? Can we predict from it? So on and so forth. Okay, so that's the Eucalyptus public cloud, and you've seen it work. I have to say another thing that you've experienced is, my own predilection for these kinds of talks. I've been at many grid meetings where people who build software talk with great eloquence about the software they build, and the only software you see run is PowerPoint. Okay? I think it's really important when anybody stands up in front of you and says, I build software, that you say, will you please demonstrate it for me? You. Not a minion, not someone in your group, you. You've just seen me demonstrate software that we have built. Let's talk about what happens if you want to get it. Eucalyptus, version 1.0 came out May 28th. That was 2 weeks behind schedule. We started coding February 1st. The initial impetus for this idea started basically in September of 2007 over a number of conversations I had with Dan Reed. Dan Reed and I were at a meeting, and we were talking about cloud computing, and I said, look, I think I can build this. And he said, you should build this. And I'm like, okay. And, what should I do? And we kind of hashed it out. And so it took me 6 months to sort of get my head around it, and it took us 4 months, 3 months, 4 months, to build the first version. It was binary only, and it was only for rocks. We are currently at revision 1.1. It took us about a month to come out with that. And we had to fix WS security. We got the REST interface working. We had the source code support and these guidance things. 1.2 is going to be out, we think, by Friday. Here, there's way more bug fixes. You don't have to completely reinstall. There's an upgrade mechanism. It's actually what's running on the EPC at the moment. It's a lot more stable. It's more scalable, so on and so forth. So this is really a minor release. At 1.3, we think there's going to be some better functionality. So what's that functionality? Well, first off, we understand that the networking part of this is the part that's really going to cause people heartburn. VDE, bless its soul, is a good place to start, but it isn't enough if you really want to make this into an experimental infrastructure that doesn't crash all the time. And yet, you have to be able to do this as an overlay. So this really presents us with three options. One is, we think we can exploit the protection mechanisms that are currently built into Xen for network interfaces, at least with respect to Ethernet, to implement what amounts to a Xen-based software VLAN. Now, that's an awful lot of words. What it does in terms of advantages and disadvantages is it makes it a software-only approach. So essentially, all we're doing is very, very carefully controlling the Xen configuration through the available Xen interfaces on your machine. So we don't reach in and start mucking with the networking. But what it breaks is the thing that we've tried really, really hard to do, which is to make the system hypervisor independent. And you would need this kind of Xen-based support in order to make this work. So we're debating that. The other way, and this is certainly the way that gives you the most flexibility, is to sort of bump it up a level. Instead of working at the VLAN level, you work at the IP level. And this has some lovely advantages. IP tables and NATs are well supported by most installations, and you can program them dynamically and so on and so forth. The problem here is that a lot of installations have their own IP table configurations. And so now what you've got is this merge problem where you want to put things into the IP tables dynamically. They've got a static IP table installation that they don't want you to violate. You've got to make sure all that works, and then that's got to be dovetailed with whatever NAT infrastructure you've got. And again, the possibilities for collision and annoyed system administrators go up with this solution. The last solution, and this is the one anybody who is doing this for real would really want, is to essentially hope that your cluster switch supports VLAN trunking. And Cisco does, others do, but Cisco's interface is really good. In fact, you can program Cisco's interface dynamically. So what you really want to do is have Eucalyptus just issue VLAN configuration commands to your switch and have it all done in hardware for you. And that is going to be fast, and it's going to be scalable and probably secure. But your system administrators are going to have to allow an open source software project to come in and begin reprogramming the internal switch fabric. And I know our system administrators, and the UCSB students here are smiling at this moment, will never, ever, ever agree to that. So, but there are lots of people who are interested in this, and so we're going to do it. So I think we'll probably wind up doing all three. I think this is going to be out in 1.3, probably by September 1st, and then these two will probably wait for a 2.0 release. There's this question of hypervisor secularism, and in particular, we've really worked hard to use a small subset of the libvirt interface. Libvirt is an open source package that abstracts virtualization commands from Xen, VMware, and KVM at the moment. And so in theory, since we're programming to libvirt, we should be able to run native on VMware and native on KVM. We haven't tried this. There's just not enough hours in the day. Frankly, just based on some very anecdotal experimentation, I think this is going to work and this may not, but it's close. What does work, what we have actually tested, is to stand Xen up inside VMware. That works miraculously. And then if you have Xen running in VMware, you can run Eucalyptus. But that's an awful lot of mechanism. This is really the right solution, so we're working on that. And then we have just started to look at this, Hyper-V. The virtualization interface that you all have come up with looks really good. It looks like it's a very, very powerful interface. It looks like it's very doable for us. Not a huge amount of shimming and refactoring. The tricky part is the networking. We don't understand what the Hyper-V replacement for those networking approaches might be. So we're working on that. And one of the questions I have is whether Hyper-V actually has support for VLANs in it. If I were building a hypervisor today, that's the first thing I'd put in. That's the thing that's missing. Hypervisors need to know that virtual machines talk to networks, right? Hypervisors know virtual machines talk to disks, but they don't know that virtual machines talk to networks. And so, and that's silly. So anyway, we need to understand that. Also, we need to understand whether Eucalyptus will run in .NET. We went with the Apache mechanisms, and it's not clear in the web service community how portable that stuff is. Right? If you take something out of Apache and Access and you drop it into .NET, does it work out of the box? We don't know. We're going to find out. We're going to try to stand up a campus cloud. So we're part of the UC Cyber Infrastructure pilot, and we've got a test installation running at UCSB in the California Nanosystems Institute. But basically, if we can get the VMware thing working, we can run on the student workstations all over campus, make it look like a cloud. That should be interesting. And the big part here is an accounting system. No one's going to let us do that until we can actually figure out how to do credentials management in a way that doesn't drive people crazy. And we're working on that. There are projects that have begun to spin out of Eucalyptus. One is Google App Engine. So it turns out that App Engine, which is really Bigtable and MapReduce through a Python interface, if you want to think of it as a layered system, will run inside EC2 using this tool called AppDrop. Google makes a home edition of App Engine available. The Bigtable implementation is not very scalable. Okay, so we have a student. There's a student who's actually working in Chandra's group who is porting AppDrop to Eucalyptus and then porting App Engine to HBase and/or Hypertable. These are scalable, two-dimensional Bigtable implementations in the open source community. If all this works, you will be able to take Eucalyptus and this package and run something that looks like Google on your clusters. That should be interesting. RightScale. This is a company, a local company, that makes Ruby on Rails configuration tools for EC2. And initially, we went to them and said, look, we need you to be our Turing test. We need you to point RightScale at a Eucalyptus installation and break it so that we understand the ins and outs and the corners of the interface that we simply can't test because we're not testing them under some sort of programmatic control. They've done that. They didn't break it. So now, apparently, you can point RightScale at the Eucalyptus public cloud and start configuring systems. And great. I mean, that's part of the open source uptake that we're hoping for, is that other organizations, projects, so on and so forth, begin using the system either as a service or in terms of software. Lessons we've learned. Open source cloud computing is an interesting idea, but it's really a different thing than cloud computing as a production quality service. You've got to worry about portable software. You have to worry about architecting something that can live in anybody's infrastructure. Right? One of the big differences between grid computing and cloud computing, for example, is that in grid computing, we bought off on the idea of federation day one. We believed there was no way that any central organization could control the configuration of the resources that the grid was going to run on. That is not how cloud computing is done. Cloud computing purveyors believe in their souls that they do control the configuration. Amazon controls the configuration of EC2, and they will forever. That's their business model. So if you take that as an initial tenet, you architect a really different system, So we're more in the grid computing space in that we have to run on everything without knowing what that thing is before we get there. And most cloud vendors are not in that space. So the architecture is different. I mean, multi-cluster ensemble is not something, another thing we learned, is not something that a lot of people have access to. So this isn't MySQL. Everybody wants to do relational databases, but not everybody has 3 clusters that they want to turn into a cloud. And so there's a different level of expertise and user community, if you will, for this than we first anticipated. And there are not very many tools for that. This is just strange. I mean, a lot of people want to run this on their laptop. Okay, we've made it work, but that's not something we anticipated. We thought, why would you ever do that? The answer is we still don't know, but they do. So it works. System administrators in the real world still do this all by hand. We thought rocks, yes, this is a cluster tool. It's used by the National Science Foundation supercomputer centers. Everybody at NSF is happy with it. Nobody who uses rocks to manage systems complains about it, right? I mean, that user community really likes it because it makes their jobs a lot easier. Nobody in the, quote, real world cares. They're all doing this by hand with scripts, configuration files, blowing it with the IP addresses, so on and so forth. A lot of the discussion in email we get is, I'm getting the stack trace back. What does it mean? And the answer is, it means it can't find your credentials file, right? Okay. So that's interesting. I mean, in HPC space, the most expensive resource is the system administrator. We can get money to buy machines typically. We can't get money to pay competent system administrators. And so the real world is much more build from source and sort of hack your way through it than it is automated. That was interesting. This is something that is absolutely true. There are no, as far as I know, cloud configuration tools available. If you think about Red Hat, if you think about Debian, if you think about CentOS, what they are automatic methodologies or automatic systems for making your machine into a Linux box. You get the kernel, you get the packages, and they're not compatible, right? Converting a Red Hat to a Debian is not something that you can do, but these are all different tools for doing that. You make a single Linux image. What ROX is essentially that functionality, a packaging and deployment mechanism for clusters. Clusters are different because there's topology. There's a head node and there's a back end node, and not all the networks are considered the same, and not all the disks are considered the same, and these things all think everything's the same. So ROX is the next step. What's the cloud version? Multi-cluster, virtual machine provisioned, doesn't exist. There is not an evolution here. I don't know of a project, something called Puppet. Puppet is CF Engine. It's good. CF Engine's good. CF Engine is a wonderful way of doing maintenance. It doesn't help you much with installation. So there needs to be some work done here. I don't know if we'll wind up doing it or not, but it doesn't exist. And with about 3 minutes left to go, I will conclude and say thank you to the National Science Foundation, and in particular the VGrads project, of which Dan Reed was, until his joyous journey to Microsoft, a PI. San Diego Supercomputer Center, CNSI, Indiana University, and Rice University, all of whom have helped us along the way, rightscale.com. These are the people who are responsible. Sriram is one of them, sitting there in the back, for better or worse. This is me, and that is our webpage. And I will stop and take any questions you might have. Yeah, wow, how's that possible? This is the future, right? I mean, read the blogs. You want a story? We released Eucalyptus on May 28th. June 2nd, I got an email from a guy who, Serge Patel, who blogs for something called OStatic and GigaOM, which are two sort of technology blogs following cloud computing. And he said, tell me about your project. I'm like, yeah, okay, well, here we go. He says, oh, this is really great. I'm going to write a blog entry about it. June 2nd. 16 hours later, Facebook tried to recruit my entire group en masse. 16 hours, right? And I heard this, I went, what? And it went from those 2 blog postings to like 500, right? I mean, there is a tremendous machine out there behind this. When was this did not happen in grid space, right? We've built a lot of grid space software. We've got users all over the world for our grid tools. 16 hours, no one came to me and said, wow, your batch queue prediction thing is so great. Let me recruit your group. Yeah.
So what kind of options did you give your students to keep them from going to Facebook?
That's the question everybody asks. I don't know. I'll tell you why I think they didn't go. Okay, I think I can answer that question. The people, many of whom are in this room, who do this kind of work, are both really excited by the challenge and also visionary enough to know that if Facebook calls in 16 hours, Microsoft's going to call someday. And maybe, and it's not like Facebook's going to go away, right? It's not like, these are not, this work is not done by people without some amount of vision for the future of this technology. You employ many of them. You are employing at this moment many of them, and you're happy to hire more. Absolutely. So are other folks. And so I think what they correctly did, and I'm very proud of them for this, right? I'm really proud of them. What they correctly did is they kind of said, look, we just started this. This is going someplace. We agreed to sort of see this through. I mean, we have had, I will say, in our group. And Sriram, can correct me if I'm wrong. We have a timeline. Version 2.0 is going to be out mid-September. We're basically going to take this through some version of version 2.0, and then we're going to evaluate what's next. Is this a career? Is this a company? Is this done? I mean, what happens? And I think with that kind of support, with the idea that they could actually see what the roadmap is and decide for themselves, it seems to have made sense to all of them to stick around. They still get calls, not en masse. The fact that it happened so fast and that they didn't contact me, right? I'm insulted, right? Wait a minute, hang on a second. There's other people on this list, namely me, and no, they don't want to talk to me at all. Yeah, and I went to Velocity, which is this O'Reilly conference, and I talked about this. And Velocity is populated by these lots and lots of startup companies, people with new technology ideas. It's really fun. Everybody's very excited. And first question out of everybody's mouth was, is that really true? Did they try to recruit your group? And the second question was, why didn't they go? Yeah, I don't know.
One question about the long-term vision of this.
Mm-hmm.
So you are building a whole new cloud infrastructure from scratch. So compared to like doing some research on cloud, say like intelligent resource allocation.
Yeah. Why would we do this? Yeah. Well. No, that's the point. Yeah. So, right. Very, very good point. Let me see if I can rephrase this question. Rich, you're a college professor. You're not doing any research at this moment. What's wrong with you? Yes, I understand that. The answer is we now have an infrastructure nobody else has, and we have the experts. If you want to do cloud computing research, and you're not one of these people, you're going to have a hard time competing with them for publications. We know exactly what works. We have users. We've got, the EPC is instrumented. We know what the internals of clouds look like. Nobody publishes that. So in terms of a research vehicle, this is a Ferrari at the moment. Now other people are going to come along, and that's not going to last forever. ASPLOS deadline is Friday. We know that. NSDI, so on and so forth. The reason to do this in an academic group is because it gives your students a research opportunity that they wouldn't otherwise have. And that's why there's a finite deadline, right? At some point, either these people have to go off and do something else, perhaps in the commercial space, or they have to go back to being researchers. We gave ourselves essentially this summer to do it. Yeah?
This doesn't apply to astrophysics, but when a company puts its crown jewels on somebody else's computer, what do they do to stop extra leaks of information?
Yes. Absolutely great question. And so, I think this is fundamental. I think that's an absolutely fundamental question having to do with cloud computing. So the question is, you might be willing to outsource the computation. The computation's volatile, but you're probably not willing to outsource. You may not be willing to outsource the data or the management of the data over which that computation takes place, because the data actually has value and it persists. And so from our perspective, that's another argument for having something like Eucalyptus, right? What one would probably want in a commercial sector is an infrastructure that runs inside their enterprise on their data, and then a similar infrastructure that is hosted by a commercial service where the programs and the environment is the same, and it's just where is the data that matters. That's technically possible with Eucalyptus and EC2 at this moment. You can run a Eucalyptus cloud on your resources. Your programs, your environments, your images, all of that stuff, that's going to work inside EC2. You just have to figure out where you want to put the data. Do you want to put the data inside EC2? Run inside EC2. If you want to leave the data where it is, run Eucalyptus. The other nice thing about Eucalyptus is that interface is modular. If you give me the WSDL for Blue Cloud, I'll do Blue Cloud, right? If you give me the WSDL for, some other cloud infrastructure that may be coming out soon, I'll do that. I mean, there's no reason you can't make this interface compatible at some level with other cloud mechanisms. There are serious questions about scale, right? You're not going to be able to run 100,000 machines inside a single Eucalyptus cloud in your environment. We're not intending for you to do that. But you can control the data and make the environment that you have on your infrastructure look like the remote environment so that you ease the software development and migration process. That's our hope. Other fantastic questions? Yeah.
So how do you ensure that performance guarantees that are given to a particular client or a virtual machine, they are always met?
Right. Great. It's an SLA question. So I can tell you now or in the future. Now, the way you ensure that is by making sure that your system essentially is never oversubscribed, and that if it is, that you just tell the user it's oversubscribed. Okay, so for Eucalyptus, what that means is if the cloud controller, lays these image requests down on your resources, and when there are no more slots, it says no, failure, right? And in some sense, that's what EC2 does. Now, an important thing to understand about this sort of at a larger scale, and this is a research question we are well qualified to investigate. This is, in fact, the research that I was most interested in doing when we started this project. You have this statistical problem associated with SLAs that I don't think is well understood outside academic circles. SLAs are probabilistic. Batch scheduling, which most people don't think of as being probabilistic, absolutely is probabilistic. There is a probability that PBS is not going to run your job. There's certainly a probability distribution, in fact several, governing how long your job waits in the queue. So if you're going to do SLAs, you really have to start thinking about things probabilistically, and nobody does. Okay. We spent a lot of time developing new statistical techniques, new time series analysis techniques for doing this kind of probabilistic influence on the fly in this environment. And we think we can do things like look at the history of load in your system and predict whether at some target probability you should agree to host this SLA or not. That's just a matter of predicting how much offered load there's going to be in the future. And we've had really, really good success in really bad environments of making those kinds of predictions. So in point of fact, what you want to do is build a probabilistic mechanism into the SLA engine, right, that understands which SLAs can be instantiated when. And you want to make that be associated with a success probability, 3 nines, 4 nines, whatever, and we think we know how to do that. Now, I think, in defense of Amazon, I think that's what they're doing. And if you look at the way clouds are structured, it's very interesting. It's very different than grids. In a cloud environment, you have many, many users, but the amount of resource that a user can get is very small compared to your total resource pool. That's completely opposite from a grid. A grid, you have a small number of users, but almost all your users can ask for all the resources, right? So from an SLA perspective, what Amazon has done is turn the prediction problem into predicting essentially what's the user growth. Because they know the biggest thing any user can give you is 20 requests, and that's a small fraction of what they've got. So user growth is probably very slow. Things that are slow are easy to predict. So you can actually get into this SLA prediction business, and that's probably what they're doing, right? Whereas in grid space, you can't. And so we actually have technology for doing that kind of thing very, very fast, much faster than what the user growth curve is like. So we think we can actually expand the size and make something that kind of looks like both a grid and a cloud simultaneously. Other fantastic questions. You've been very patient. Thank you very much.